The science of cooking. Heat transfer plays an integral role in our everyday lives, but most people aren't aware. Common phenomena that occur in every kitchen are convection, conduction, radiation, and boiling. Convection, conduction, and radiation all have constituent equations. Solving for boiling heat flux is a bit more
The
complicated.
type of heat transfer is convection, and in one place we see convection is in an oven. Convection is defined as the heat transfer due to bulk flow. Now there's two types of heat transfer. There's natural and then there's forced. Natural is just as it sounds, and it just occurs naturally. It's like air going over any type of plate or anything, any solid, liquid. Now forced convection is a little bit different and it occurs in an oven. In an oven, you have heat being put into the oven from the coils and then a fan blowing that heat so it heats up whatever you're cooking so it cooks faster. Now convection is defined by Newton's law of cooling, and to find the heat transfer rate, which is Q, you need a couple variables. Some of the variables are the heat transfer coefficient, which can be found in any table in any chemical engineering textbook or Perry's Handbook for Chemical Engineers or online. Another variable you need is the area, and in this case you'll need the area of the oven inside. And finally, you're going to need the temperature gradient. The temperature gradient is defined as the temperature of the surface minus the temperature of the surrounding, or T infinity. Now for an oven, T infinity would be the temperature we set it at, and for us we're going to set it at 200 degrees Celsius. And the temperature of the surface would just be ambient temperature, which we're going to find as 25 degrees Celsius. So the units for convection are in watts when you use area and watts per meter squared when you don't include area in the equation. So in this oven right here, as I mentioned, you have the area, which would be the area of the oven, and we have our plate, which we're going to take as the temperature of the surface, so the temperature of the surface of this plate. And then when we close the oven at our set temperature at T infinity, which is 200 degrees, we're going to be able to find the heat transfer rate or the heat transfer flux. To solve for the flux in an oven, you need to use Newton's law of cooling. Newton's law of cooling is simply Q double prime, which is your flux, is equal to H, which is your convection coefficient, times Ts, temperature of the surface, minus T infinity. In our case, H is equal to 17 watts per meter squared Kelvin. And for T surface, we're taking ambient temperature, which is 25 degrees Celsius. So that would be 25 degrees C plus 273 to get it to Kelvin. And your T infinity is equal to 200 degrees Celsius because at 17 watts per meter squared, your temperature is 200 degrees Celsius. So you do minus 200 plus 273, and you get for Q double prime is equal to negative 975 watts per meter squared. Yep.
Conduction is defined as the heat transfer due to under-molecular motion. In cooking, when you are cooking just a beef, could be an example, one, it follows Fourier's law, and to find the heat flux, you could just multiply the thermal conductivity by the temperature gradient, and that will give you the heat flux in watts per meter squared. And to find exactly the heat transfer, you just multiply it by the area of the plate. To find the heat flux through a pan, we could just use Fourier's law, which states that the heat flux is equal to the negative thermal conductivity multiplied by the temperature gradient divided by the distance or thickness. For the frying pan, we have the thermal conductivity of negative 237 watts per meter Kelvin, and the temperature difference is just equal to 300, which is Ts minus 25 degrees Celsius, which is the temperature of the ambient, divided by the thickness, which is equal to 0.02 meters. The heat flux is equal to the negative 30. So the heat flux is equal to negative 32,58750 watts per meter squared. You could see that the heat flux is very large first because we have a large thermal conductivity, and also our temperature gradient is very large.
Radiation is the third type of heat transfer. All objects both emit and receive radiation, and the emissivity of an object is its effectiveness to at emitting radiation. This is usually assumed to be the same as its absorptivity. which is its effectiveness at absorbing radiation. Today, we're going to use this microwave to heat up a bowl of water, and using radiation's constituent equation, which is the heat flux is equal to the emissivity times the Stefan Boltzmann constant, which is the amount of heat emitted by a black body. Black body is an object that is emitting radiation but not absorbing any. The Stefan Boltzmann constant is the amount of energy that a black body, or the amount of heat flux that a black body emits. It is 5.67 times 10 to the negative 8 watts per meter squared Kelvin. The Stefan Boltzmann constant with the heat flux and through an object and the emissivity of that object allows one to find the temperature difference between the surroundings of an object and that object. The constituent equation for radiation is heat flux is equal to the Stefan Boltzmann constant times the emissivity of your material times the temperature of your surroundings to the fourth power minus the temperature of your material also to the fourth power. Now, for the microwave, we have your total heat exchange rate is equal to 70 watts. So to find the heat flux, you would do 70 watts times the total surface area of your bowl of water that you are heating up, which is going to be equal to a diameter of 10 centimeters and a height of 4 centimeters. So you would do pi times 10 times 4 plus pi times 5, your radius, squared. Your Stefan Boltzmann constant is equal to 5.67 times 10 to the negative 8th, and the emissivity of water is equal to 0.993. And the temperature of your water when it begins is going to be equal to 23 degrees Celsius or 296 Kelvin. And once you've solved for your effective temperature of your surroundings, this is going to be the temperature of the walls of your microwave, you get 715 Kelvin or, 442 degrees Celsius.
The last part of heat transfer in cooking is boiling. We use boiling for almost everything, especially with cooking pasta. Boiling occurs at two interfaces. Most people think it's a solid and liquid interface, but it's actually two different types. It's solid liquid and solid vapor. Now, other characteristics are the latent heat effect and pressure, large amounts of heat transfer and small temperature differences, and finally, a convective heat transfer coefficient. The different boiling modes. First, let's go over what is boiling. Boiling is when evaporation occurs at the solid-liquid interface, and occurs when the temperature of the surface is greater than the saturated temperature. Next, transfer of heat from the solid to liquid interface. The flux is equal to Newton's law of cooling, which is the heat flux is equal to H times Ts minus Tsat, and bubbles form and detach from the surface. Next, mixing occurs. You have pool boiling, which is free convection and bubble mixing. Next, forced convection occurs with forced convection boiling. And finally, the temperature becomes subcooled and then saturated. Now, with boiling, you have different temperatures, and eventually you get to temperature saturation, and your temperature of the surface goes over the temperature saturation, which then becomes the temperature excess, which is the difference between temperature surface minus temperature of the saturation. And after, what occurs because of this is different boiling regimes. The first boiling regime is free convection boiling, which occurs at temperature excess of less than 5 degrees Celsius. You have little vapor formation, single-phase natural convection, and your H is a free convection correlation, which will be found later in Chapter 9. Next, you have nuclear boiling, which is 5 degrees Celsius is less than the temperature excess, which is less than 30 degrees Celsius. What occurs at nucleate boiling is isolated vapor bubbles, liquid motion strongly is impacted by bubble nucleation, and you have a large increase in H, and also jets and columns. Right here we have free convection boiling, and as you can see you have little vapor formation and small bubbles forming at the surface. Here we have nucleate boiling, which is characterized by the jets and columns of water and the bubbles that are forming at the top. Now that we have nucleate boiling, you can actually start cooking some pasta. After nucleate boiling, we have transition boiling, which occurs between 30 degrees Celsius excess temperature and 120 degrees Celsius of excess temperature. A fraction of the surface is covered by vapor foam, and H will decrease with increasing temperature excess. Finally, we have film boiling, which occurs at temperature excess is greater than 120 degrees Celsius. The heat transfer by conduction and radiation occurs across the vapor film.